Howdy. The purpose of this video is to explain the concept of an activated process. We might also call this thermally activated process or an Iranian process. So what is this? What does it come from? And where do we encounter it in material science? And it turns out that it pops up all over. So if I'm talking about nucleation of a solid phase, for example, ice, from either a liquid or a vapor, in both of those cases, we would describe that as an activated process. If I'm talking about a concentration of mobile charge carriers in a semiconductor, that also is described as an activated process. And finally, if I think about concentration of defects or diffusion, these also are examples of activated processes. So it touches a lot of different phenomenon in material science, especially in the realm of kinetics, when you're talking about how rapidly does something occur. So let's think about activated processes, and let's think about it around an example. And so we're going to talk about diffusion, interstitial diffusion. And in this case, we're just going to talk about an atom moving from one site to another neighboring site, right? It's hopping from the left to the site over here to the right. And we're going to think about this conceptually using what's called a reaction coordinate. And this plots energy on the vertical axis and the progress of the reaction on the horizontal axis. So this could also be thought of as time in certain cases. But we're going to think about the initial state. And the initial state is at some energy level, right? The absolute value doesn't really matter in this case. It's more the relative value that we're interested in. And then we'll think about the final state. And in this case, this final state is essentially going to have the same energy as that initial state. The only thing that's different is that the site is moved over one unit, but everything else is pretty symmetric about the example. So that would lead us to believe that the final state should have the same energy as the initial state. But something has to happen to go from the initial to the final state. We can't miraculously disappear and reappear. So in this case, this atom would have to squeeze its way between these two other atoms. And you can see they're pretty close together. So in order for that to happen, this one would have to move a little bit down, and this one would have to move a little bit up. And that intermediate state, if I were to draw it here, so I can just draw those middle three, when this white atom is squeezing its way in between the other two, is a pretty high energy position relative to the initial and final state. So we're going to draw that like this. We can think about this as an energy barrier that we have to overcome in order to go from the initial to the final state. And the smaller that energy barrier is, the easier it is to overcome it. The larger it is, the more difficult it is. So remember, in this case, atoms are always moving around. They always have some little bit of energy. So at a finite temperature, we can say the energy of the system is proportional to kT, where K is the Boltzmann constant. And so the probability of this event happening is going to be proportional, well, it's going to be exponentially proportional, actually, to the ratio of this activation energy over kT. So this term here is the activation energy. Sometimes it's also called a heat of some sort of reaction, heat of vacancy creation, heat of diffusion. So you can see different variables used to describe this. But this is the magnitude of that energy barrier we have to overcome. So if E sub A is smaller, it's more likely to happen. If the temperature is higher, it's also more likely to happen. And that's because, in this case, that's because a higher temperature means there's more energy in the system. These atoms have a lot more motion, lot greater vibrations involved. And it's more likely that this one will vibrate up, this one will vibrate down, and this final one, this middle one, will have an opportunity to squeeze through and move from that site to the left, from the left to the right. So remember this ratio, the activation energy over kT. We could think about another case. In this case, if I'm going from I'm going from a pure liquid to a pure solid. And if I'm below the freezing temperature of water, then I know the pure solid is the more stable case. And so there's going to be some difference in energy. But I do have to go through some intermediate state. And in this case, that's related to the formation of a small particle called a nucleus, and the fact that the surface energy is really high for these nuclei. So again, we have to go from an initial state to a final state. In this case, there's a difference in energy between the two states, but I can still talk about an activation energy, a barrier that I need to overcome. And so I need to get past this small nucleus state to the point where it's able to spontaneously continue growing. So again, for this process to happen, the rate at which it occurs, or the probability of forming a nucleus and that grows to a larger crystal, is going to be related to E over KT. So it turns out that these are exponential relationships. And this comes from the statistics of the system. If you look at the distribution of all the states that the system is likely to take, then there is some small number of states that has enough energy to overcome this activation energy. And that number of states is given by this term, exponential of minus, in this case we're going to use Q sub D, so that's the heat of diffusion over RT. We're using R instead of K. This is just a unit conversion. But right, so the important thing is that the process is not linearly proportional to this ratio. It's actually going to happen exponentially proportional to the ratio. So, well, let's go back. Let's work our way through these other things. So now we're going to move on to a different example. This is diffusion. So the rate of diffusion, the diffusion coefficient, D, is going to be proportional, so there's a pre-exponential constant, to the exponential of the activation energy over RT, where again, T is going to be the absolute temperature. So you have to make sure that this is in Kelvin scale. If you're using a Celsius scale or a Fahrenheit scale, you're going to get a wrong answer, because this always needs to be in terms of an absolute temperature. So when we're looking at activated processes, if we want to measure some data and determine these variables, for example, what is the activation energy for a system, we are going to do that by plotting log of D on the y-axis and 1 over T on the x-axis. Now, this is because if I think that the process is going to follow this relationship, if I take the log of both sides, if you remember your logarithmic rules, this guy I can bring out. So I can say the log of A times B is the same as the log of A plus the log of B. If I'm taking the log of an exponential, so this x is shorthand notation for e to the something power, right? So the natural log of the exponential of something simply equals the something. So if you're not familiar with this, go back and brush up on your exponential and log mathematical rules. But this results in the following relationship. And I can see immediately that this is going to be a linear relationship, right? Y equals, in this case, B plus mx. So y is log of the diffusion constant. So if we call x, if we let x be 1 over t, then the slope equals negative q over r. And the intercept equals log of this pre-exponential factor. So if I were to plot data, and we can measure these things, if I take two materials and I put them together, and I watch material A diffuse into material B, then I can measure the change in the diffusion coefficient as a function of temperature. And if I plot log of D versus 1 over T, I will get a linear relationship. And from that, I can come back, I can look at the intercept, and that will give me the log of the pre-exponential factor. And I can look at the slope, right? M equals the change in log of D, right, that's on my y-axis, over the change in 1 over t, that's on my x-axis, and that is going to be equal to minus q over r. Okay, so we've talked about the mathematics a little bit of the Arrhenian relationship, but we also talked about where it comes from. It comes from the fact that we have some sort of energy barrier that we have to overcome. And as a system heats up, there's more energy in the system, and so it's more likely for this forward process to happen. Also, if the energy barrier is smaller at a constant temperature, it's more likely for this process to happen. And when you consider the statistics of these sort of processes, they give us this exponential relationship to E over KT, or over RT. Finally, we work through how to determine activation energies from data. Ideally, you would want to make your plot where you're looking at the log of something. In this case, we're looking at the log of the diffusion coefficient, and we're plotting it versus 1 over t. And we need to look at the slope in this kind of a plot.